Hi, welcome back to another episode of Real-World Serverless, a podcast where I speak with real-world practitioners and get their stories from the trenches. Today, I'm joined by AJ Stuyvenberg, who is the AWS Serverless Hero and a staff engineer at Datadog. And you've been hanging around on social media. You've probably seen some of the work that AJ has been doing around the Lambda co-stars, which we're going to dive into a bit later. But before we do that, AJ, do you want to just say a few words about your work and what you do?
Hey, Jan, thanks so much. I really appreciate being invited on the show. I've been a fan of Real-World Serverless for a long time. It's great to be here. Yeah, I'm a new AWS hero just this year, but I've been working at Datadog for a few years now. And before that, I was an engineer at Serverless Framework. Worked on kind of some of the open source stuff and some of the various enterprise SaaS products as well. My background is sort of in SaaS products, building teams and building services for all kinds of different SaaSes. And then most recently in the last probably 6 years has been focused entirely in the serverless side of things. I'm an open source developer. I've got a couple of projects that plug into the serverless framework and kind of a popular library that helps make the new HTTP streaming response for AWS Lambda a little easier to use if you're a TypeScript developer. And yeah, I've just been really interested in serverless ever since I first picked it up. Now at Datadog, I'm a staff engineer in the serverless group, and I'm responsible for building the libraries, the tooling, the Datadog Lambda extension, everything that gets telemetry data, out of your Lambda function or your Cloud Run instance or Azure Container Services, any of those kind of function as a service systems, and getting it back into Datadog. I've been there for a little over 2 years now. It's been great.
I was aware of some of the things that you were doing around the serverless framework before as well. And one of the things that I think Datadog has been really good for the community is the state of serverless report that they've been doing for a few years now. I don't know if you're involved with that, but a few things on the report for 2023 kind of piqued my interest. So I want to get your take on some of this.
Absolutely.
So for the folks who are listening in on the Spotify or podcast platform, we are going to be looking at the state of serverless report. So don't worry if you can't see it on my screen, but you can just go to the report that's linked in the description below yourself and check it out for yourself. So AJ, can you see my screen now?
Yeah, everything looks great.
Okay. Yeah. So I think this fact number one is interesting to me because for a lot of us, myself included, we kind of expected the serverless to at some point just explode, do like a massive exponential growth. But it hasn't been the case, but rather it's been kind of this kind of pattern you see, very gradual. But a lot of companies, especially running on AWS, are doing some kind of serverless. But it's not like a big sea change, but rather it's been a small gradual uptake. Even though a lot of people are doing serverless on AWS, it's probably still a very small part of the architecture as opposed to like a complete overhaul of the entire architecture to go serverless. Is that similar to what you've seen in Datadog and in talking to customers as well?
Yeah, sort of. And I want to touch on the methodology for fact number one, which is we're looking at just an organization. Do they have any kind of serverless technology in their stack that is connected with Datadog? And as a result of that, if they have 10,000 Lambda functions and whole teams that are entirely serverless, or if they just have one, they're going to show up in this number. And I think that impacts the growth rate. So, we're seeing, 74%, 73% of our organizations are using serverless in AWS in some way, which means that I think that's representing like the maturity of the maturation of serverless. There's still a lot of growth in the other clouds in Google and Azure. However, we're seeing a 3% growth rate on the AWS side. Azure and Google grew 6% and 7% respectively, which just tells me that orgs are adopting it when they need it in their stack. I think we chose this representation because there's a number of other ways we could look at it, like how many functions they deployed or how many functions have they invoked, or what exactly means serverless. But we wanted to make sure that we're kind of encompassing a lot of these services we use. So in AWS, that's like Lambda, App Runner, Fargate, and CloudFront functions, which are sort of the function as a service, and then the more serverless compute methodologies. I would say that I don't think I would expect super explosive growth, because once we're in the high 70% of organizations adopting serverless, you're going to, like getting to that last couple percent is just a heavy lift. There's a number of organizations that are using AWS that just have to run a VM or just have to, maybe use an S3 bucket, and they maybe have no need for that compute. So I think what this really shows is that, yes, it's still growing. No, it's not like 100% of all organizations are using serverless, but I do think that explosive growth has probably already happened, and we're seeing this like maturation where it's continuing to be used more and more.
Yeah, the Google part is interesting because Google has not really been pushing serverless very much. It's still very much on the container train, whereas Azure has been, at least from what I can see from the outside, has been promoting functions as a service quite heavily. But the adoption rate has, I guess, it's much lower than I kind of expected to see at this point. Is that because things like Cloud Run gets included in the Google's metrics here as well?
Yeah, we are including Cloud Run. So for Google Cloud, we're looking at Cloud Functions, App Engine Flex, and Cloud Run. I think that containers versus like functions is maybe not the way I would frame it, especially given that AWS Lambda functions can run on containers and have for some time. So instead, it's just more, do you really need that serverless compute scale to infinity, scale to zero, and no pay for idle, which is kind of the key. I think the key feature set a lot of people are chasing and adopting. As far as Google goes, I think they are pushing it. I think they're doing a pretty good job too. You're probably seeing just lag time, right? Because I think AWS Lambda has been out the longest. It's probably the most mature. And other serverless services, not just Lambda, and we're not tracking them here, but like S3 is like the original serverless service. And I think SQS was the very first service AWS launched, if I recall correctly.
Yep.
And in those cases, like, yeah, they've just been around a long time. So they're going to have a lot of growth because people, by nature of picking those clouds, are going to pick those kind of core services. And I think Google is just a little later to AWS in some of that area. I don't necessarily think it's a result of what people want or what people are necessarily pushing. It's more of, time. It takes time to adopt something into your stack.
Okay, sure, that makes sense. And I guess down below, there was another fact about the Google. I think this one, right, is talking about the Google Cloud Run being by far and away the most popular in terms of adoption across, compared to, I guess this is probably looking at the AWS Fargate, perhaps?
Yeah, so this is what we're looking for in fact number 2, or what we're bringing out, is that Google Cloud is really leading this fully managed container serverless adoption. They as a second mover into the space, they have a lot of advantages. Cloud Run is able to learn from Lambda, and other services, of course, other things Google have done, like Google Cloud Functions and Cloud Run V1. But I do think what's called out here is extremely indicative of why that growth is so high. And it's that container-based serverless platforms really simplify adoption and migration. So if you already have a container and you're using a container to deploy something to Kate's environment, and then you see, okay, this thing is barely running at all, we can probably offload this and run it on demand. It's very, very easy with something like Cloud Run or App Runner or Azure container instances to like move that stuff over to these container on-demand container services without having to worry about any of the orchestration or any of the other work that goes into K8s. So I do think that's what you're seeing here is there's a lot of growth because, unlike Lambda, which had never really had a great lift and shift story, where you have to migrate to this like function invocation response methodology. In a lot of cases, you don't have to run a web server in your container or in your zip file. All these different things that happen in Lambda don't have to happen in these container-based applications like AWS App Runner, Google Cloud Run, or Azure container instances. So you're able to just drop a container in more or less and have it run at usually a more cost-effective scale for lightly used services. And I think that's why it's just super easy to migrate. And I think that's why they're seeing a lot of growth there.
I guess we don't see the breakdown here, but I'll be quite interested to see the kind of the breakdown in terms of AWS adoption for things like App Runner versus Fargate. Because Fargate was for a long time the kind of poster child for fully managed the serverless container, platform on AWS. But one of the things that I was missing from Fargate was always the ability to trigger it with some kind of event without having to have something else in front of it, like EventBridge or something else. Whereas Cloud Run was able to do that out of the box. So have you seen the underlying data in terms of for AWS, whether or not there's like a lot of this use adoption is driven by App Runner, or is it mostly still Fargate?
Yeah, I couldn't really comment on what the underlying points are. We're going to kind of share what we have here. However, I personally really like App Runner, and I think as developers we sort of sleep on it because we're so used to Fargate, and Fargate's been around for so long. But now with AWS's charging for IP addresses and IPv4 space, I think that App Runner is going to be more attractive because it comes with a free load balancer. So you pay instance hours. So if you're a developer who's using an application to play around with or work on a side project and you shut it off and you're not using it, App Runner can be the cheapest way to deploy like a container-based application on AWS and play with it. And it because unlike Fargate, where you have to pay the monthly fee for a load balancer, which I think with an IP address is something like $25 or $30 a month. I don't know. I can double check that. But with App Runner, you get that for free and you pay by instance hour. So it's cheaper at that rate. Like I said, I don't know and can't really comment fully on the breakdown for all of these, but we know, that App Runner is a much newer service compared to Fargate. So I would definitely expect Fargate to be more popular. Anecdotally, I think you and I both see that mostly on social media too. Like Fargate's been around a long time. A lot of people use it, rely on it, and like it. But I do think we're going to see some growth with App Runner and other container instance services kind of across clouds, especially as people try to phase out IPv4. And if they're charging for it the way AWS is, that'll definitely impact that at some point, especially among the like hobby project developers.
Yeah, especially for when I think a lot of people would complain about spending $1 or $5 a month, on the AWS side projects. I guess one of the things that's was it Corey Queen that blogged about the 27 different ways to run containers on AWS?
Yeah, I think it was 17, but maybe it's more now.
Right. Yeah, I think his favorite container service was Code Build or something like that to use that to run containers on a schedule, which I find is quite funny. Again, it's probably the easiest way to put a container and get it to run without having to worry about the VPCs and things like that.
Yeah, absolutely. And I mean, with Fargate, you have to think about a VPC as well. So there's definitely more there.
Yeah, every time the networking gets involved, I just find myself always sinking a lot more time than I sort of budgeted because debugging network connectivity issues is just never easy. So I guess going further down the list, there's a few things that which I think makes a lot of sense, like a front-end development platforms. We've seen the last couple of years, platforms like Vercel and the Netlify has done really, really well. We are seeing people like Fastly and Cloudflare doing more and more with the workers, I guess functions at the edge. And I guess this one is not surprising either. Node.js and Python still the most popular. I'm kind of surprised by how many people are using Java. I guess that's a sign of the maturity of the Lambda platform that enterprises and the people that have been running Java for decades are now starting to use Lambda with Java. And I'm guessing
I think you're exactly right on that. Node and Python have always been very popular. They've always been languages that serverless developers have loved. Seeing Java and custom runtimes kind of jump up this list in recent years, having been involved at the last, I think, 3 State of Serverless reports, is pretty impressive. And I think you nailed it. It's highly indicative to me. I look into that and see, enterprises are adopting serverless in a really big way. I think on the AWS side as well, they're clearly making huge investments into Java's runtime. Snapstart is the canonical example for Java 11 Corretto. Now you can really melt your cold starts by using Snapstart. One thing that we know about Java, though, is that there's usually a lot of runtime reflection. So not all of that time is built into initialization. However, it does improve what were previously pretty painful cold start times. Snapstart does. So AWS has been investing in it. And I think as enterprises are picking it up, that's going to become, a harmonious cycle.
Yeah, I've seen a few people reporting on the Snapstart, and that they've been able to get the Java functions to cold start within, a few hundred milliseconds as opposed to, 4 or 5 seconds in the past, which is quite impressive compared to some of the experience I've had running Java functions. I think in the past I was seeing upwards of like 10 seconds cold start with like a Scala functions, which is completely crazy. So basically it makes it unusable for anything that's user facing where someone's going to be waiting for that response time. So it's only good for like background stuff. So I guess that kind of leads us nicely to the cold start thing about Java, which this does surprise me a little bit that it's only 2.7 times longer, where I would have expected a bit more. I think maybe the methodology here is partly to explain, because I think this I was looking at the definition down below that this is only using this is only looking at the init duration. And I think for Java is slightly different compared to Python and Node, because some of the class initialization happens during the first warm invocation. So there's probably still some other additional cold start impact that's not accounted for here, but it still seems quite promising that the Java is now within some reasonable distance to Node and Python. So I guess this is mostly to do with the snap start. Do you see people using provision concurrency a lot nowadays?
Anecdotally, I do see a lot of folks using provision concurrency, and I think that's for a bunch of different reasons. I think obviously the biggest is to ward off cold starts, but I also think that a lot of people are choosing to run legacy applications in Lambda and just want it to be ignored and run at a fixed cost, which is like a relatively fixed cost known monthly, and then they have 1 month of a lot of traffic and then it can scale up, which I think is exactly what Lambda is for. Your point on init duration, yeah, we're looking at init duration here. We have other ways of looking at this data, but we certainly want to ensure that we're showing things that users see and having some consistency there. So what I do think is important to note here is that like you said, Java specifically has runtime reflection. So specifically the static initialization phase doesn't always include all the time it takes the application to start. This is also true. We see this in container images as well, where the sort of, I've noticed in this talk I've been working on that container images, the very first invocation takes a significant longer period of time to run before subsequent cold starts are much faster. So I do think that provision concurrency is a way to get the performance you need out of your application when you just need Lambda to run it, which is great. I think that's exactly what it's for. It doesn't surprise me that the layout of these cold starts are the way they are, with like Python and Node kind of being the fastest for as far as the popularity of the libraries we see, like Java between the three, right? Java, Node, and Python. Java is definitely the slowest. We said 2.7 times longer than Python. But I still think we're seeing a lot of new development there, and we're going to see this number change a lot in the next year, and that's why we want to keep an eye on it. We also call out proactive initialization here, which is something we'll be looking at a lot, probably in next year's report. And these are spillover initializations where, due to the traffic shape calling into AWS Lambda function, you may end up with a pre-warmed Lambda function that doesn't have an invocation, which is just like a free warm start, more or less. And depending on your application and depending on the shape of the traffic and how busy the given worker node is and a number of other variables we can't control, it's a performance benefit for all of us, which is great. I wrote this blog post about this in July, and AWS has since updated the doc, so I should probably revisit it. But effectively, it's just a really simple query you can run in Datadog if you want. You can also run it just in CloudWatch and take a look at these cases where Lambda warms up your function before you have an indication. You can observe these. They're super easy to observe. With a kind of high throughput API use case, we saw between 50 and 80% of our initializations were actually proactive. So the user who hit that cold start didn't actually experience it because initialization happened before the request was even made, which is neat. I also worked with Ken Collins, who's another AWS hero, working on the Lambda project for bringing Ruby on Rails to Lambda. And he saw very similar results, which is pretty cool. All of these vary. There's nothing you can do about it, so there's nothing you should do about it. Just kind of enjoy the fact that this can happen. If you're using an active tracing service like X-Ray or Datadog, you can see these gaps, and that's a big part for why we wanted to document and explain this. But we do see this a lot, and it's something that I think customers are going to see a lot too.
Yeah, this blog post was great, by the way. I really enjoyed reading this. I was able to see some of this in my own environment, and from talking to AWS Lambda team in the past, that they kind of been hinting at some of this a little while back. But it's good that this is fully, it's really well documented by you here. So anyone who's interested about understanding how this proactive initialization works, please go and check out AJ's blog, which I've linked here, as well as in the description below. Another thing I saw you done recently, which I found quite interesting, is you've done a lot of investigation into cold start behaviors. especially for around the container images, which we talked about earlier. And I think specifically around the one that really piqued my interest was the stuff you did around Bun, which is just a new JavaScript runtime that this offers, I guess, superior performance, but because it's not a natively supported runtime, so you have to run it on a custom runtime, which has some cold start penalties, let's say. And but you were able to, I guess, to talk to Jared, the creator of Bun, and to figure out that some of that worse performance was coming from not using the correct build for the Bun runtime. And I think you also saw that by packaging it as packaging your Lambda function as a container image. Which I guess I should probably just say, just in case the people are misunderstanding this, when you use a container image with Lambda, you're not running a container inside Lambda function. You're using it as a package format for your function in terms of the content that you want to upload to the Lambda service. But that allows you to have up to 10 gig of a package instead of the 250 meg normal limit with zip files. But they're also doing some very clever optimization, which in this case, you found that actually allows you to cold start a Bun function in, was it 130 milliseconds or something like that?
Yeah, in the best case, we were able to see a cold start in around 120 milliseconds for Bun. Let's rewind and talk about, so I'm working on a talk for AWS reInvent. If you're going, please sign up. It's COM 305 in the session catalog. And the title is Demystifying and Mitigating AWS Lambda Cold Starts. So I'm all about cold starts. A big part of, I'm all about distributed systems performance, and it's a big part of what Datadog does every day. It's a big part of my team. It's a big part of my work. And when we talk about improving the median performance of any service, we often look at the P99, or like the 99th percentile of requests. In Lambda, those are almost always cold starts. So we look for ways to mitigate them. We look for ways to observe them. One of the features that we shipped that is, I think, pretty useful and innovative is cold start tracing. It allows you to see the dependencies that you're importing and how that impacts your cold start time. So with that out of the way, I'm working on this talk. And one of the questions I get a lot, both through Datadog and just people on social media and at conferences, is how does the code that I provide impact the cold start time of my Lambda function? So I've been investigating that. I've been working on a Twitch stream and YouTube, and also LinkedIn. Don't sleep on LinkedIn. Streams, which are going over all of these various configurations and package sizes, and then the initialization duration, and now also like the round trip time or the full request time of Lambda functions at like no dependencies, 0 megabytes all the way up to 250, and also container images. The container images have really piqued my interest because earlier this year, Mark Brooker and the Lambda team put out this amazing paper about how the Lambda team made container image-based Lambda functions run and execute and start as quick as a zip function can start. And while I don't see that 100% of the time consistently, I do see some really impressive data. And what they're doing in a container image is two parts, I think, that are most important. The first is they're doing something called convergent encryption, and then they're doing a tiered cache. So convergent encryption, the idea is when you push an image to ECR, and then you attach it to a Lambda function, or you deploy a Lambda function with that image, it will divide all of your container image into 512 kilobyte chunks. And it will encrypt them in such a way that they can consistently hash and compare 512 kilobyte chunks with other customers. So what we can do is very clearly understand the parts that are shared with other people, of which is super common, where most people are using common base images. Maybe you're using, the provided AL2 base image, or using like the Node.js base image or Python base image. Hundreds and hundreds of customers are doing the same thing. So instead of having to copy each of those different container images from each of those different customers' repositories, when a function loads, they're able to say, okay, 90% of these chunks we already actually have on the worker. Actually, I think the cache density is really interesting here. So if we take a look, I'll pull up the paper. They do a 3-level cache, right? So this is the paper. It is called On-Demand Container Loading in AWS Lambda. Mark Brooker, Mike Danilov, Chris Greenwood, and Phil Pivanka, sorry if I got your name wrong, Phil, wrote this paper. And it's awesome. It came out earlier this year. Definitely read it. they're talking about why container images are more complex to load. So the first is that conversion encryption deduplication without trust, where we can share chunks of data, and that way not all of these bytes have to be streamed into the sandbox when they start. The second thing they do is a tiered cache. And this is where the real magic, I think, happens for this cold start time to be so low with a custom runtime or container image. So there's a worker level cache, an L1 cache. Then there's also a cache in an availability zone. So for every region that's divided into like 3 or more AZs, each AZ or each physical building, physical data center has a cache in it for container image chunks. If that chunk isn't there, then we go to the source, which is an S3 bucket. The AZ cache, they say, is pretty standard. It's a least recent used algorithm, and it's just fetching those chunks over HTTP2. One is in memory for hot chunks, and then a flash tier for colder chunks. So you get this trimodal distribution where somewhere between, say, 50% and 90% of your container image is already on that machine when you upload your Lambda function. And actually, I think the key takeaway here is that 80% of everything you upload to Lambda, if today you create a brand new container-based Lambda function and put your own dependencies in it, put your own project in it, and upload in it, 80% of those bytes you upload, AWS has already seen and it's already cached, which is amazing. That's such a great stat. So you have this really high cache density or cache hit in Lambda, which is why they're able to load these very quickly. So getting to Bun, to answer your question, what we did to improve on the current times that we've seen for cold starts is kind of 3 things. The first, you can provide Bun as a binary, and actually they publish a script in their repo, so you can create a Lambda layer for Bun. So it's really easy to grab like a runtime.ts file that integrates with the Rapid client in the AWS Lambda runtime, so you can kind of get that drop-in experience you're used to as a developer, where you just write a handler.ts or handler.js file, and it will invoke it when it needs to be invoked. That's one part of it. They already provide that. So the second part that we can do in the layer, or we can do in the container image and in the layer, is they compile the Bun runtime along with the Lambda runtime code they write. And you can do that with bun build -- compile. So that will embed the bun itself along with your runtime code in a binary. So that's one thing we do to improve it. The second thing we do is when me as a customer uploads like the handler.ts file that we're used to uploading, which is just exporting an async function like you would normally do in JavaScript, is we can actually pre-build that for Bun. And we can even build that into all of it. So it's a kind of a step beyond tree shaking and bundling like you're used to, where it will actually pre-generate the byte code that Bun needs to run your Lambda handler upfront. So that's how we can really improve the performance. And then the big gap, or the big jump in performance and getting down to that 120 millisecond at best cold start, has been just using a container image, because we know we can take advantage of this caching strategy, which isn't the same strategy or isn't the same level of sophistication that they have for zip files or for Lambda layers. So yeah, at best we saw 120 milliseconds. We've kind of seen them all over the board. With no additional code, we've seen cold starts as long as 1 second, which is pretty typical, right? Like those bytes have to hit that AZ cache and also have to get onto the worker. But once they're on that worker, if you have a repeat cold start, maybe in that node or at least in that AZ, we're seeing really low cold starts: 121 milliseconds, 359 milliseconds, 136 milliseconds, and so forth. That obviously changes as you add dependencies. However, it's telling me that if you really want to use Bun, it's definitely viable in Lambda today.
Yeah, that's really interesting, because I think you mentioned that there as well, there's a huge swing depending on which cache you hit, whether or not you hit the L1 cache or maybe the L2 cache. And I'm guessing as more and more people using the Bun with container images, your chance of hitting an L1 cache or L2 cache is going to improve as well.
Yeah, exactly. And that's true for any dependency. I think that's why, for example, if you were to measure, or if you look at our Datadog's cold start tracing product, the time to take to load the SDK out of the runtime versus the time to load it when it's packaged and maybe gzipped or ES built yourself, the runtime is going to be a little bit faster because it's cached. Because other people are going to use AWS SDK, as a dependency, and those bytes are going to be pre-divided, chunked, and cached. I did another blog post about the same thing where I talked about benchmarking the AWS SDK. Here we were using this cold start tracing feature that we built for Datadog, but you can very clearly see the difference between loading like the entire V2 SDK out of the runtime versus like bundling it yourself. And if we go down to the conclusions board, you can sort of see if you load the whole SDK from the runtime, it'll load in about 320 milliseconds. But if you package it yourself and upload it, it's going to load in 540. And this is with a zip file, not a container image. So this chunking and caching strategy isn't necessarily at play. But because these bytes are already baked into the runtime, presumably Lambda has a cache of those as well. So with container images, maybe we'd see this even out a little bit more, where these bytes, because other people are also doing the same thing. They're also, packaging the AWS SDK in their container images. You would see a more consistent result if they're cached. But yeah, you're totally right. Like going back to Bun, the more people who use Bun, the more likely that it is that you're going to get bytes on that worker already in your container image. Yeah.
Yeah, and I guess that caching behavior also explains why in the past I've also seen the AWS SDK that's packaged or bundled as part of a Lambda layer loads faster compared to when if you just use the SDK that's been bundled in your deployment package zip file instead. So I guess with the layers, because it's shared across multiple functions, I imagine that also gets cached somewhere as well along the way.
Yeah, that is interesting. I saw a post from Julian Wood replying to something about what I've been streaming, which is just like benchmarking cold start performance, about how there is some amount of caching for both function contents in the zip archive, which I think they're unzipped after you deploy, so they don't have to be unzipped live, but those contents are cached in some way, and also layers are cached in some way. The quote from Julian, or I don't want to quote, but like the message from Julian was that it's not nearly as sophisticated. It's not nearly at the same level as the caching they had to do for container images. So that tells me there's probably still some performance that can be gained from here and some improvements. And really, we should go back to, this is the beauty of serverless. This is the whole reason we're picking these technologies to run our applications, because I didn't have to invent this 3-tiered caching scheme, and I'm certainly not on call for it, but I can take the advantages of it and put a brand new runtime like Bun in it and know that, maybe that very, very first cold start is going to be a little slower, but after that, they're pretty reasonable. And improving the platform is a huge part of why we use these services. Yeah, that happens for us.
You just get the performance improvements over the years without having to do anything, which is the kind of the best optimization you can do, right? And on the file system thing, I don't think Lambda actually unzips the files, because remember they actually use this compress the file system, so it can literally just mount the file system. Yeah, that's it, zipfs. I do remember there's also another thing you mentioned though as well, that you found there's no difference on the init duration based on the package size, and I think that's also because that mounting of the zipfs file system happens before the init duration. In the past, I've done a bunch of other performance tests on cold starts myself, and we actually found that the amount of time that happens before the init duration starts counting, there is a difference between, I think that's what Julian was talking about, where the first invocation after a deployment, it takes longer if we measure the end-to-end latency compared to the subsequent cold starts, because of must be some caching of the zip file that you're loading. But also find interestingly that the memory size has an inverse impact on cold start, presumably because if you want to say allocate a 10 gig function, is harder to find a space on an instance on a worker somewhere compared to if you want to allocate 128 meg instance of a function. So we found that the bigger memory actually has got a longer cold start time that's not part of the init duration. I wonder if you have seen something similar to that as well in your tests.
I've certainly experienced that. I haven't seen enough to draw concrete conclusions and share them in a way that I feel comfortable with for some of these other ones. I would say if you're interested in learning more about that, I'll be talking about that at reInvent. I do want to give AWS, like the team, time to read what I'm working on. I send them everything before I publish it as just a courtesy. I sent them my proactive initialization post like 3 weeks before it came out, to just, like I said, as a courtesy to them. I wouldn't surprise me that a 10 gigabyte function is harder to place in a distributed worker fleet because it takes more resources, takes more memory, takes more vCPU. So the service that the Lambda placement service, I think is the anecdotal name I've seen for it, is going to presumably take a little bit more time. Having run a couple of large distributed systems at Datadog, it wouldn't surprise me that there's sort of a sweet spot here. And 128 is probably the fastest one to find space for. But one of the most common mistakes I see new users making is just leaving the default function at 128 and then loading a bunch of code, and they don't get an error. And I think a lot of users expect to get an out of memory error immediately, but a Lambda function, especially in init, will swap. It will happily swap to disk while it loads your dependencies. So you need to keep an eye on, if you're just using CloudWatch, my first piece of advice for new developers is you got to keep an eye on the memory used and max memory in the report log line. If you see those two values are equal, first off, you are in danger of being killed because you're running out of memory, or like killed, right, out of memory. But also, even if not, you're probably having suboptimal performance because that, as those bytes are being allocated by either your runtime or your own code, you've got to swap some of the memory out and write it to like a RAM disk for new memory to be allocated. So totally, like there's absolutely that component of it too. So I would believe, my suspicion is we'll see a sweet spot somewhere in there. But I have experienced what you're describing, where like a 10 gigabyte function actually takes, in some cases, more time to cold start with the same amount of code as a smaller function, for sure.
So in that case, what would you say are some of the top 5 most common mistakes that people make when it comes to optimizing for cold start performance? Because you mentioned something. Okay, go on.
Let's give away the secrets of the talk before I give it at reInvent. Probably the first mistake I see users make, especially with JavaScript, is importing the entire AWS SDK. This is common. Most blog posts you see when you're learning how to do something in AWS, like write to DynamoDB, you'll see something like const AWS equals require AWS SDK. Now this is a call from the V2 SDK, which isn't built into like submodules by default, but you don't need to load the whole SDK. When you do this, and for folks who are able to watch this like on YouTube are able to see, there is a long directory of clients that Node is going to load. And if you only need one client, you can actually reach in there and grab just the client you need. So the difference of that is literally a little bit of extra code. Instead of requiring just the AWS SDK, you can require AWS SDK / clients / and then the client you want. Then in my example, I'm loading SNS. And we can see that the difference between those two calls is hundreds of milliseconds on your iteration time. So if we just grab one client out of the runtime, it's about 104 milliseconds in my testing. But if you load the entire runtime, the entire AWS SDK from the runtime, it's 324 milliseconds. It's like 3x slower just from a tiny, simple code change. So I think number one, that's the biggest thing, is make sure you're only loading the code you need into your Lambda function. Number two is overcomplicating the deployment or overcomplicating your packaging. There was this weird phase serverless developers went through, which hopefully we're past, which is believing that Lambda layers are free overhead. Like you could just put dependencies into your Lambda layer and it doesn't count to your limit. That's not the case. For any zip-based Lambda function, which are Lambda layers only support zip-based packaging, the total amount of your code and any layer you add, all added up, has to be less than 250 megabytes. That's a challenge for a couple of cases. Using Lambda layers too early when you're not sure you need them, I think, is mistake number two. They add a lot of complexity to packaging, and then they certainly don't improve your cold start time because those bytes have to be loaded at the end of the day. Number three, and I guess these aren't that much of an order because I'm kind of riffing here, but number three is the RAM issue we discussed earlier. Swapping at init is going to hurt your performance more than probably anything else. So make sure you keep an eye on the memory you're using. And
on the memory thing, though, as far as I know, during init the duration, Lambda runs at full power. It's not limited to the, but I guess that's just a CPU, not so much the memory. Because you're talking about specifically the memory pressure and
exactly.
Okay, gotcha.
Yeah. So let's actually talk about that too. Lambda doesn't publish this, but Michael Hart a while ago did a great blog post about how you get an uncapped vCPU during initialization, and then afterwards you get whatever equivalent vCPU you have in for your step of memory. So in Lambda, memory and CPU are linked. They don't publish what layer or what level memory gives you additional vCPU. There is some nuance there. However, we anecdotally, I think everyone has seen this and seen the post, and AWS hasn't refuted it. So I think it's pretty well understood that you get a certain amount more CPU during a init. But yeah, specifically when we're talking about memory allocations and the RAM you're consuming, if you are seeing that the RAM you're using is up to the limit that you've configured for that function, what's happening is your function is going to heavily swap depending on how much more memory you have to allocate. So that memory has to come out of memory, written to disk, and new bytes have to be allocated, which can be really, really painful for your cold starts. And I think a lot of people don't even realize that. For many toolkits like CDK and SAM, 128 megabytes is the default, or if you just upload a function to the console or use like Terraform, 128 megabytes is going to be the default memory configuration. And yeah, you're going to have more painful cold starts with that. Finally, so 3 and 4 most common issues I see with cold starts are probably people putting code in there and loading it and never using it at all. This goes back to only package what you need. We talked about with the AWS SDK. I see on a multi-week basis, multiple times a week, I see a helpful developer who went out and built a package to publish to EventBridge, and maybe that includes the entire SDK, right? Just on accident. Or I see production builds that have open API, right, where you're generating like a Swagger doc every time your Lambda function runs, just to do that. And I see that more and more with those like mono Lambda APIs, where you're taking an entire API you've already built and sort of copying into Lambda and routing with the like routing internally with something like Express or something like Flask. And then yeah, probably the fifth one for cold starts that's most common is taking old patterns, like having to put a giant request router into your Lambda function and using that all the time. And if you look at an application that most people are going to run in Lambda, in many cases, the distribution of requests to that function are not equal or not even normal. What you see is one route, maybe get timeline feed. If we're building like a Twitter clone, that will be the most hit route, or like get user or get tweet. You can break those out into their own dedicated functions and not load any of the other code you're loading. That's a really big improvement you can just make. The other one is lazy load. So I wrote a blog post about this as well. And especially with what we've talked about, mounting the zipfs and how that can improve your cold start time if you don't load the bytes you don't need. One thing you can do is conditionally load dependencies. So if you have a user, in this case, my example is API gateways talking to AWS Lambda, which is then writing to DynamoDB. It's a REST API, but we have this, particular user, which is me in this example, needs a message to be published to SNS as well. Loading that SNS client, initializing it, making the connection, all of that takes time. And if you don't have to do that for every request or even most requests, it makes sense to put that in a branch and just say, okay, if this request is for AJ, then let's load the API. Let's load the SNS SDK. And by doing that, once it's loaded once, it's memoized, like the node runtime keeps it around. So you don't have to reload it. Even if you call the method again, it'll be loaded. So there's an advantage there. But finally, you make it so that the person that has that special case is going to pay that performance impact. And again, there's a little bit of nuance here when it comes to how much CPU you're getting. So we can clearly see that during initialization, where we have that theoretically full vCPU, or maybe simply more CPU power, we see that the SNS client can load in about 50 milliseconds. However, when we defer this to runtime, when a Lambda function requests the SNS client, we see it loads in about 80 milliseconds. And this function specifically, I think, is running in 1024 gigabyte, or 1024 megabyte or 1 gigabyte of RAM. So I would expect to have a little bit less vCPU. They published that 1769 is the magic number to get one full vCPU in Lambda, and this is under. So this is exactly what I would expect to see as a result. So yeah, that's probably the last tip is, unlike your applications that are load balanced, where maybe you can load everything up front and then put it behind the load balancer and start serving traffic, in Lambda, that time is always going to be felt by users. So you may as well figure out which requests need which dependencies, and you could use that as a performance improvement.
Yeah, on the memory thing, I still stick to just 1 gig of memory as default. And there's just no point in optimizing because most of my functions just don't have enough traffic to make a big difference if I switch to 124. But I think 128. But I think AWS does that classic AWS thing where they be really conservative. So all the AWS centric tools like CDK and the SAM, they just choose the default. That's make sure that you're not going to spend any more than you absolutely need to as a default. Whereas I think the serverless framework's default is 1 gig. It just makes a lot more sense because 99.9% of the time I just don't need to optimize. Just like maybe like a handful of functions need to get optimized. And on that mono function thing, I actually had a client. They had an API that does some server-side rendering with React, and then some REST endpoint. And they brought me in, and one of the questions they had was, why is our REST endpoint taking 5 seconds to cold start? And when I look at the functions, oh yeah, because you got the React being initialized every single time, even though you're hitting a REST endpoint. It's the kind of things that, like I said, is really easy mistake to make unless you understand how the sort of Lambda's performance and behavior is different from a more traditional serverful environment. So you have to kind of architect your application accordingly. And I guess that goes back to the thing we talked about earlier, where Lambda just doesn't have that good lift and shift story compared to containers, and that's why things like Google Cloud Run and things like that are getting really popular. Yeah, so those are some really good advice, and I think those are very consistent with stuff that I've seen in the past as well. I guess on the bun side of things, actually, so on the tooling side of things, one other thing that kind of popped out in that state of serverless reporting was how popular Terraform is, which I did not expect. But I guess now that now that I think about it, it absolutely makes sense for large organizations where they have a mix of just pure infrastructure workload plus application development. I guess that makes sense that Terraform is still so popular over there because you kind of want to just use one tool for both, even if it's not, it doesn't give you the best for your application development. And I have to say, CDK is less popular than I thought. I thought CDK at this point would probably have overtaken serverless framework just based on the amount of noise and people and things that you see on social media. So any feedback about in terms of your personal observations about what people are using and of where things are going in terms of deployment tooling?
Yeah, absolutely. And I think there's a lot of ways to kind of explain both the Terraform side and the CDK side. My interpretation of the data, again, this is just me here, Terraform is super popular amongst enterprises. So it would not shock me if there's more or less a rule that is, if you want to ship something to production, you will use Terraform. So if you want to use serverless, I think developers are probably pretty happy there because it's really not a bad production experience. I think there's a lot to be desired in terms of the development experience that Terraform has for Lambda functions. I think you and I probably both agree that local emulation is hard and fraught and there's a lot of risk, and testing in the cloud is probably the best way to ensure that your software is going to run the way you expect it to run in production. And I think that can be hard with Terraform because you kind of have to go through this big Terraform plan, Terraform apply step on every iteration. However, it doesn't surprise me one bit that as you have, we're using host count as a proxy for size of their organization. So as you approach hundreds and hundreds of traditional instances, it doesn't surprise me that you tend towards Terraform because I think that's just very common. Compliance is mandatory. It's not an option for organizations. So if they already have everything, like the hard parts of their compliance and risk management figured out with Terraform, it doesn't surprise me one bit that they're just going to use that on the far end. As far as CDK, especially compared with serverless framework, CDK is, if you think about V1, V2, and SAM, and just pure CloudFormation, serverless framework has been around for all of that. But CDK V2, which is the current supported version of CDK, is really new in comparison, especially compared to serverless framework, which launched at reInvent in 2015, I think V1. So it's just a matter of time. I think we'll see that start to grow. I think we'll see a lot more. Hopefully, I would like to see a lot more variance in terms of tooling, with people picking tools that they really like that work for them. I do think calling out CloudFormation separately here was an interesting choice that we sort of had to make because serverless framework builds CloudFormation. CDK builds CloudFormation. So really, you can see CloudFormation is just the big winner out of all of this. And then it kind of boils down to, are you using CloudFormation or are you using Terraform? But regardless, I'm really excited about this result. We're looking at a bunch of other tools as well that are super popular. Chalice is sort of a new upstart. We're looking at like SST or serverless stack, which is popular. There's a number of tools for this that are kind of growing. And I'd love to see more. I think what I'd really like to see is another kind of tool that compiles to CloudFormation, but also can take CloudFormation and then interpret it in its own native language. So, if you could write a language or like a grammar that is backwards parsable for CloudFormation, that's super cool. And I believe that the app composer can do that. You can like plop in CloudFormation and it can start to show you, each of the squares, which I think is super neat. But I'd love to see another tool that does that.
Yeah, there's still a lot of, room for innovation, and there is a lot of innovation happening in this space. I was just talking to Matthew Bonnick the other day, and he also talked about Winglang as well, which is this new tool from the creator of CDK. Honestly, Chalice was one of the first deployment tools that was available for Lambda. I'm surprised it's still hanging around for.
It's had a resurgence. Yeah, that's why
it's actually more popular than SAM. It's crazy.
Yeah.
But yeah, I think was it that thing about enterprise having a rule around Terraform. I've definitely seen that in some enterprise clients. Sometimes to even the extreme that the app team will be the feature team will be working in, say, server framework, but before they deploy it, they have to hand it over to the infrastructure team to rewrite it into Terraform so that it got one place that records every single resource that gets provisioned and pushed to production, which to me is just completely crazy and backwards. But like I said, there's some companies, some enterprises does have that rule that says you have to use Terraform if you want to go to production.
Totally, doesn't surprise me at all.
So I think I've been really interested to read to go through this report. So many things that like even this one, the number of organizations that uses Lambda functions VPC, that also surprises me as well. Really good job. Thanks for doing this and sharing with the community every year. I'm really looking forward to the 2024 and see what's going to happen there.
Yeah, absolutely. Thank you, and thanks for having me on. I'd like to leave listeners with just a little note. If you're going to AWS reInvent, definitely check out my talk. It's COM 305 or COM 305 in the session catalog. We'll be talking all about AWS Lambda cold starts and cold start performance. So if you care about the P99 performance of your Lambda function, it's a good talk to go to. I hope you enjoy it.
Yeah, I've left the link to the session catalog as well as the name of AJ's talks down below in the description, so you can go and check it out yourself. So AJ, thank you so much for coming on the podcast and sharing your experience about serverless and how to optimize Lambda cold starts.
Yeah, absolutely. Thanks for having me on.
No worries. Hope to see you sometime soon.
Yep. See you in Vegas.
Okay. Bye-bye.